Welcome back again, folks. We are talking about the cosmic microwave background and recombination. So in the previous lecture, we got done talking about x of T. T is temperature and x is the fractional ionization, which is simply the ratio of the number of free protons, or which is also the number of free electrons, divided by the total number of baryons. And we're going to sort of arbitrarily call recombination as the time at which x is equal to 1/2. So if in the previous video I said s, then that should hopefully clear things up. So x is 1/2. That means half of the protons are in free ionized form and half of them are bound up in neutral hydrogen atoms. That's going to give us at least a scale of the temperature at which the cosmic microwave background is formed, and then we'll make one more correction to that, and we'll be in good shape. Okay, so what do we have? If x is equal to 1/2, then what that means, so at recombination, and I'll put this in quotes, right? This is just to give us a sense of scale. X is equal to 1/2, and that's apparently equal to -1 plus the square root of 1 plus 4s all over 2s. I'm not going to do the algebra for you, but I'll simply let you know that with the algebra, you'd find that s is equal to 2. You should verify that. And if s is equal to 2, then what that means is, well, s is given by this quantity, so I'm going to let this be equal to 3.84 times eta. Remember, eta is the baryon to photon ratio. It's a tiny number, and it's multiplied by this quantity, kT, all over mass of electron, c squared. This is raised to the power of 3/2, and then exponential of q over kT, where q is the binding energy of hydrogen. It's that 13.6 electron volts. This is true at the particular temperature of the recombination temperature, and that's what you would like to be able to solve for. Now, I don't want to dwell on this, but I do want to spend about 2 minutes just giving you a sense of how you could possibly solve this equation. If you're looking at this and scratching your head, you might wonder how in the world you solve this, and there is no exact analytic solution. This is called a transcendental equation, right? It's something that has a power law and an exponential. But we can suggestively rewrite this, and if we're lucky, we can solve this perturbatively. So I think it's worth just sketching out how that would work. If you rewrite this, you basically want to rewrite this in such a way that you can identify the variable that you're trying to solve for. The motivation is we're trying to solve for the temperature, which sort of, it shows up here. In fact, you might as well solve for K times the temperature. It shows up here and here. You might as well also include a factor of Q there. So if we could solve for the quantity Q over KT, or KT over Q, then we might be able to do this. So here's what I would ask you to do. Verify that you can do this. That you could solve for e to the q over kt, have that on one side. And then on the other side, you'd have 2 divided by 3.84 over eta. And then you'd sort of cleverly insert a q. You'd multiply by some factor of q, divide by a factor of q, so that you could write this, and then get rid of the q by writing it like that. Okay, it's something you're allowed to do. And what that allows you to conclude is that everything out front here, this is just some number. You can get that. And then what you're left with trying to solve for is this ratio, Q over KT. That's what we can actually solve for. So you can, in fact, rewrite this as e to the, let's call it w. I just acted like I didn't know what I was going to call it, but I already made notes. E to the w is equal to some number. That number I think I wrote down. It doesn't matter. Let's just call this whole prefactor a. So this is all equal to a to the power of w to the 3/2. Okay, it's still a transcendental equation, but it's easier to look at. Let's go ahead and take a natural log of both sides of that equation. You might guess, at least from the left-hand side, that's how you would try to solve for w. What that means is that w is apparently equal to, remember what the rules are for logs, this is log of a plus the log of w to the 3/2. That 3/2 comes down, and therefore that's log of w. Okay, we haven't really done anything new. This is still a transcendental equation, But if it's true, if that this term is big or small, well, in this case, you might guess it's big. Does it dominate? Is this a small correction? If so, you're in luck, because then W is approximately equal to the leading term, natural log of A, plus 3/2. What do I do with natural log of W? I take the natural log of this expression. In other words, the natural log of what's in there? Well, it's the natural log of A plus, and then you could keep doing this ad infinitum. But why don't we just write the word small correction in the hopes that we get to ignore it. So let's just ignore it to give us some approximate solution. This is how you could figure out W perturbatively, and then you could get your recombination temperature. I'm just going to leave it at that and let you play around with this. It turns out that this is true. In other words, according to what we've done, X is equal to 1/2 when the temperature is equal to what we'll call the recombination temperature, and that turns out to be about 3760 Kelvin. So we're getting a sense of the scale. Maybe between around 3,000 and 4,000 Kelvin, we would have the universe go from opaque to transparent, perhaps. By the way, this corresponds to having a redshift of approximately 1400 Z rec equal to 1380. If you're wondering where the hell that comes from, remember that there's something you can do. You can say that the temperature at any given time, we'll write this as T rec, is equal to the temperature today divided by the scale factor. You could write the scale factor as a function of time or a function of Z. I don't care. Let's write the scale factor like this. You can always rewrite the scale factor if you're comparing today's quantities to earlier quantities. You can write the scale factor as the inverse of 1 plus Z. In other words, this is 1 plus Z. And so let me add some little subscripts. This is scale factor at recombination. This is the redshift at recombination. Today's temperature, we know that's the cosmic microwave background temperature. That's roughly 2.7 Kelvin. And anyway, that's how you would relate that recombination temperature with that redshift. All right, here's the thing though. This is, we've definitely made some progress, but this is still not good enough because photons, even when the universe is half ionized, photons are still going to scatter like crazy off of charged particles. Even when X is down from 1/2 to 1/10, you're still going to get photons scattering. So to do this even more precisely, we need to compute the photon scattering rate, and we'll compare that to the Hubble rate. So this will hopefully not be too unfamiliar to you. The photon scattering rate, this calculation is a pretty generic calculation that you would do for any particle interacting with other objects. Photon scattering rate. Whatever this rate is, one particle is, let's say, flying through some field of objects. So for this, what we've got is the rate of photon interacting, that is the number of collisions, number of scatterings per unit time, is going to be given by the number density of objects that it can interact with. Number density, and at least to this order of approximation, it can only interact with charged particles. Number density of charged particles. Now, every time it does that, it's going to interact with a probability dictated by, remember, that cross-section, which we've interpreted this from classical mechanics as being a geometric cross-section, but here it's a particle physics cross-section. So we multiply this by the cross-section of photon interacting with charged particle. That's what we started talking about, or that's what I had given a brief discussion about earlier on. So this is cross-section of interaction. And then lastly, it depends on how quickly this particle is moving through that field of other particles. That determines how quickly it can interact, so we need to multiply this by the speed of that particle. And if you check the units, it all works out. So what do we have here? The number of density of charged particles. Well, yeah, there are protons out there, but we had discussed that the interaction probability with an electron is much higher than that of a proton, so the only relevant quantity here is the number density of electrons. The cross-section is the Thomson cross-section with photons with electrons, and the speed of the photon is just the speed of light. So that's pretty easy. We write the rate as capital gamma. That is the rate of photons interacting with charged particles. So that is what I'll write there. what we'd like to be able to do is have this, indicate this as a function of time, or perhaps more conveniently as a function of redshift. So let's try to work our way towards that. The number density of electrons, recall that we're in this approximation where the number density of free electrons is equal to the number density of protons, right? There's only those two types of charged particles out there. The number density of protons, well, that can be related to the number density of baryons times the fractional ionization. So that's why I'll write this as fractional ionization times number density of baryons. The number density of baryons, we know how that scales with the scale factor. Let me write this as x times number density of baryons today divided by the scale factor cubed, right? That's how that quantity evolves. And then lastly, let me convert scale factor to redshift, writing this as x NB naught times the quantity 1 plus z cubed. Okay. We had learned, we had seen this somewhere, I had discussed this, I don't know if I proved it to you or not, you can certainly check that this is true. The number density of baryons today, on average throughout the universe, is approximately 1/4 per cubic meter. Meanwhile, the Thomson cross-section for photons with electrons, this is a tiny number, it's like 6.65 times 10 to the minus 29 meters squared. This is an area. And when you put that all together, that tells you that the interaction rate of photons with charged particles in the background as a function of redshift, z, is approximately given by 5.0 times 10 to the minus 21 per second times the fractional ionization as a function of z. We can do that and multiply this by 1 plus z quantity cubed. This is, by the way, Rydon equation 8. I've written this down in my notes. I think it's 8.39 or 8.35. I wish that I wrote things more cleanly. 8.39. And I think it would be good for you to verify that this equation is correct. And we will take this and compare this to other quantities in the next video.